We begin this video by describing the framework used to assess the impact of space activities on the environment. We then discuss the specific influence of the space sector on climate change. Afterwards, we take a more general look at environmental impact and their uncertainties. And we conclude by analyzing how these different aspects fit in with the growth prospect of the space sector. For the environmental analysis, the European Space Agency recommends breaking down the space sector in different segments: the launch segment, the orbital segment with the satellites, and the ground segment, and in different stages of life: the design, the raw material extraction and supply, the manufacturing, assembly, and test, the launch, the usage, and the end of life. However, in the use phase are excluded the end users of certain uses of space. Their device, for example, the television, the GNSS chipset, some sensors, some personal antenna, and services such as data analysis. In other words, what the space activities exist for. Is also excluded the digital infrastructure, network and data center that enables these uses. Although these elements are excluded from the scope of this video, they do have a climate footprint that is dependent on the space sector. So, does the space sector contribute to climate change? Yes, a first assessment produced by Wilson establishes its impact at 6 megatons of CO2 equivalent in 2018. 6 megatons of CO2 equivalent represent 0.01% of all greenhouse gases emission for the same year. It also represents 0.1% of the Planetary Boundaries Index for climate change, an index whose purpose is to quantify whether activities are sustainable with respect to an environmental threshold below a 2 degrees Celsius rise in average temperature compared with pre-industrial levels. This figure may seem very low, but given the uncertainties involved in quantifying environmental impact and given the growth dynamics of the sector we are about to discuss, we will see that it cannot be neglected. Let's first take a look at where this impact comes from. On the life cycle analysis appeared on screen. Those on the left are dedicated to complete missions, those on the right to launchers only. We observe that all stages and not only combustion contribute to climate change. These analyses are useful for quantifying the sector's impact, but they are also useful at the design stage to help make the right environmental choice. For two given space objects, the environmental impact can be different. Here are a few questions, the list is not exhaustive, to help identify ways of reducing the environmental footprint. Are manufacturing processes particularly emissive? What materials are used? What propellants have been chosen for the launch? Will the trade-off between testing and R&D is environmentally favorable? What is the lifespan, reliability, and replacement rate of the satellite? Is the satellite infrastructure shared? Or again, is the size of the TEM adapted to the need of the end users? Is the satellite adapted to its mission? Is the launcher adapted to its satellite? Addressing these issues with method during the mission design process is a methodological challenge for engineers and more broadly for agencies and investment policies in the space sector. This life cycle analysis show that all stages of the life cycle contribute to climate change, and they also show that environmental indicators other than climate change need to be taken into account, such as freshwater aquatic ecotoxicity, air acidification, and ozone depletion. This can also be seen in Wilson's graph. In addition to these impacts, to this day, the life cycle analysis, like those of ESA, do not take into account the effect on radiative forcing and on climate change of particles emitted in the stratosphere due to lack in understanding and quantification of these impacts. Here is a summary of what is known and what is unknown on the topic today for three types of gas and particles: the soot, the alumina, and the water vapor. Soot or black carbon, BC. They are emitted after the combustion of kerosene or of methane. They can agglomerate in the stratosphere between 12 and 50 km where they will absorb part of the incident solar radiation and will heat up the stratosphere. Soot's impact on climate change varies according to its heating capacity and also of the lifetime of the particle in the stratosphere and thus of their agglomeration or circulation. Soot agglomerates for a lifetime of around 4 years. It should be noted that the climate response is complex because the launchers are not homogeneously distributed around the globe. Changes in chemical composition initially occur locally. Whether in the Ross study in 2014 or in the Ryan study in 2022, soot have a proven radiative forcing effect. The alumina particles emitted by solid propulsion will absorb a part of the incident solar radiation, and should they reflect part of it, the net effect will result in the heating of the stratosphere. This effect is so complicated that it's not considered by Ryan, with Ross nevertheless attributing 4 mW per square meter of radiative forcing to it. The influence of water vapor is also debated. Is it heating the stratosphere? This is the case according to Ross. Or is it creating some polar stratospheric clouds which will cool the stratosphere? This is Ryan's result. Let's now look at quantifying the impact of these gases and particles on climate change. For these three types of gas and particle, soot, alumina, and water vapor, the heating of the stratosphere, the stratospheric radiative forcing, should be around 16 mW per square meter with a high uncertainty bar. As a reminder, the current net radiative forcing characterizing the intensity of current average warming is 1.8 watt per square meter. Ross compares the 16 mW per square meter to the value of the radiative forcing generated by commercial aviation in 2014. 16 mW per square meter, it's 25% of the radiative forcing generated by commercial aviation for just 100 of rockets. These comparisons highlight the importance of the phenomenon but have a limit. The radiative forcing generated by the particles emitted by launcher is the warming of the stratosphere. The one generated by commercial aviation is the warming of the troposphere. And to deduce an effect on the troposphere from an effect of the stratosphere, the mechanisms are poorly understood. Does the troposphere warm when the stratosphere warms? Does it get colder? Are the variations local or homogeneous? To sum up, the impact of particles on climate change is significant and includes uncertainties. Other particles emitted into the stratosphere play an important role, this time on the depletion of the ozone layer. The order of magnitude for 2009 would be to have depleted 0.03% of the entire ozone layer. This ozone depletion being caused half by chlorhydric acid and forms of chlorine emitted by solid propulsion, and half by nitrogen oxides generated by re-entering of space objects, satellites and upper stage in the upper atmosphere at high temperature. While there are many gaps in our understanding of the environmental and climate footprint of the space sector, they are all the more urgent to solve because the activities of the space sector are undergoing a high dynamical growth. The increase in the number of launches to an order of magnitude attributed to the constellation of satellites and to the suborbital flights is highlighted by 15 researchers and people qualified in the industry in order to raise the importance of understanding and mitigating the environmental impact of space transportation, especially particle emissions. Indeed, increasing the impact of the space sector without the necessary understanding is risky. Coming back to the carbon footprint of the sector, the one computed without the effect of particles. Miro, whose study focuses on a limited scope of the life cycle, estimates that growth in the sector could increase the impact on climate change by a factor of 9 by 2050, driven by constellation, space tourism, moon exploration, and space-based solar power system, with constellation playing a dominant role in the sector's footprint. As to Wilson, he evaluates the impact of the space sector at 120 megatons of CO2 equivalent, a factor 20, or an increase of 114 megaton of CO2 equivalent between 2020 and 2050. This increase would be equivalent to adding 10% of the emission from commercial aviation to the atmosphere, which could neutralize all the efforts already made to decarbonize the aviation sector in terms of private investment, public investment, and sobriety, and it can jeopardize a net zero trajectory. But are all space activities equally polluting? This is a difficult question, but one that needs to be answered at least approximately if we are to decarbonize the sector. Space missions are extremely diverse. Different types of vehicle, of data created, or service provided, involving very different quantities and very different intensities of energies. From Earth observation to low latency internet access with satellites via global navigation, not all missions have the same environmental cost, nor do they imply the same benefit or progress. To illustrate this point, here is a list of 16 very different use of Earth observation missions only. To conclude, the space sector's carbon footprint may be small today, but the knowledge gaps and the rapid growth without a clear decarbonization strategy pose significant challenges that need to be investigated. These challenges need to be taken into account right from the research and system engineering phases to ensure that the impact of the space sector on climate change is sufficiently reduced and does not undermine the effort of other sectors to meet the net zero trajectory. Your next step for training on this subject is ESA's life cycle assessment training video. Then you can consult the various publications listed in the appendix.